Good morning, good afternoon, and good evening. My name is Whitney, and welcome to our fifth one-hour session of the Arista Technology webinar series, Designing and Deploying EVPN VxLAN Networks. Previous topics have been EVPN VxLAN core route types, ARP in EVPN VxLAN, and dual homing in EVP VxLAN deployments. If you have not seen those episodes or would like to rewatch them, please visit the events.arista.com/webinars. Our sixth webinar will be on June 11th, same time, same place, so mark your calendars. Today's topic is deploying multi-tenant, multicast with EVPN OISM. Allow me to introduce our first speaker, Arista Zone System Engineer, Mitch Vaughn.
All right, thanks Whitney for kicking things off, and thank you to everyone out there making the time to attend what is the fifth installment of this tech series. As Whitney called out, today we'll be focusing on what I find to be a very interesting and exciting topic, VRF-aware routed multicast within an EVPN VxLAN deployment. Now specifically, this is via the new optimized inter-subnet multicast or OISM model. So next up in session 6, we'll leverage Ansible to automate an EVPN VxLAN deployment based on the Arista validated design. But those that have been following along may notice that there is now a 7th session listed here. And based off the feedback we've received thus far, there is a desire to see this series continue. So first, thank you all for the feedback. And for the 7th session, we'd like to open it up to all of our attendees to decide the topic. So please let us know what EVPN VxLAN related topic you'd like to see covered in session 7. Now, for those that may be joining us today for the first time, all sessions in this tech series are a live broadcast. So we'll pause from time to time throughout today with the goal of making this as interactive as possible while still keeping the session within our 1-hour time limit. And as we'll see, this will be a bit of a balancing act today as we do have a lot to cover. Also, as a friendly reminder, these sessions do build upon each other. So today's sessions will assume that our live studio audience here is comfortable with the topics covered in the first 4 sessions. So we're not going to spend much, if any, time reviewing these topics, and we may even draw parallels to them as we cover today's concepts. So as Whitney called out though, if you did miss one of the previous sessions or would just like a refresher, all of the recordings are available at events.arista.com/webinars. But as far as today's topics, the real core focus of today is going to be on 2 IETF drafts, specifically the IGMP MLD proxy and EVPN OISM drafts. Now, throughout today, we'll be introduced to 3 new route types, in addition to one that will get a fresh coat of paint with some new extended communities. And of course, with new route types comes new concepts. So we'll be touching on all of these concepts as we run through a series of scenarios and challenges today, with the eventual destination of that journey being a live scenario where we kick off some multicast feeds and essentially test our knowledge of what we've learned, specifically on how all of the pieces come together to enable, in this case, our dual-homed receiver in VRF-A to receive both the intra and inter-subnet multicast feeds across the overlay that are coming from over here from host B and host C. As usual, as we go through our scenario here, we'll make sure we validate the control plane and then ultimately the data plane with some packet captures. But here's the series of challenges we'll be working through to reach that end goal of validating this in that live scenario. So we have 5 total, and each one representing a unique problem that we need to solve in order to efficiently enable routed multicast in the overlay. So we have a lot of ground to cover, so let's actually jump right into the first challenge and let's get rolling. So since we're introducing new capabilities into the EVPN domain, we need a way for the VTEPs to signal their support for these new capabilities to each other. Now, the reason for this is really twofold. First is to ensure each VTEP understands which remote VTEPs will support routed multicast in the overlay, and the other is to ensure backwards compatibility for those that do not. Now, additionally, since the draft provides multiple options for the transport of multicast feeds in the overlay, there is now a possibility that our multicast feeds will have a forwarding model that may or may not align with how bum traffic was previously handled. In other words, we need a way for the VTEPs to signal how bull traffic will be transported between the VTEPs. So this is one of our first new terms here, bull standing for broadcast, unknown unicast, and link local traffic. Now previously we had bum traffic, but with the M removed from this equation, we still can't lose sight of the need to forward link local traffic within a particular bridge domain or EVI. And the way this is going to be signaled is via some new additions to our old friend, the IMET route. So these new additions are the multicast flags extended community, and then the PMSI tunnel attribute, otherwise referred to as the PTA. So first, we'll take a closer look at the multicast flags extended community. The idea here is that the VTEP can set a series of bits in this field that will communicate its level of multicast support to the rest of the EVPN domain. Now, in our scenarios and examples, we'll focus on the proxy bits, as this enables the VTEP to signal its support for the type 6, 7, and 8 routes needed to build a control plane for routed multicast forwarding. So now let's actually take a look at the PMSI attribute here. And this is how the VTEP is going to signal a transport method for bull traffic within the bridge domain or EVI. And we can see that looking at this, we certainly have no shortage of options here. The draft provides us with a variety of options, whether it be MLDP, RSVP, PIM, or ingress replication. Whether we're running MPLS or VxLAN data plane NCAP, we have flexibility of choice here. So let's go ahead and take a look at the new and improved IMET route in action and ultimately how it's advertised. So in the OISM model, we are enabling routed multicast at a VRF level, meaning it is enabled for all bridge domains whose subnets reside in a particular VRF. In this case, in this example, we have VRF-A. Now, because of this, we see that Leaf1 is originating an IMET route that contains the route target and L3 VNI, the route target and VNI associated with the supplementary bridge domain that is mapped to VRF-A. Now, that's another new term here. We're going to cover that more later, but for now, just know that the supplementary bridge domain is a way to ensure that all VTEPs servicing a VRF have a bridge domain that is consistent across all of those VTEPs. In other words, it's a bridge domain that must exist on all VTEPs servicing a particular VRF. So again, we'll talk about that a little bit more later in some future scenarios, but also note here in this route, in addition to the route target and the VNI associated with the SBD, we also have the multicast flags extended community on the route, indicating IGMP proxy support. Now, ultimately, this IMET route is essentially Leaf1 telling all other VTEPs in this EVPN domain, hey, everyone, I support IGMP proxy routes for all the bridge domains that exist within VRF-A. Now, similarly, if we look at the IMET route originated for the EVI of VLAN 10, we have the PMSI attributes indicating how bull traffic should be forwarded for this EVI. However, note the absence of the multicast flags extended community from the IMET route for this particular bridge domain. Now, this is because in this scenario that we have here, it's not required to advertise this extended community on a per bridge domain basis. So at the end of the day, though, ultimately what we have here is Leaf 2 and Leaf 3, once they receive this type 6 route originated by Leaf 1, they know that Leaf 1, servicing the EVI VLAN 10, VRF-A, supports IGMP proxy routes, and for this particular EVI, the bull transport method is going to be ingress replication. So we'll go through the next challenge and then we'll pause for some questions. But the next problem that we have to solve here is the placement of the IGMP querier within the bridge domain. So typically within a bridge domain, the multicast router with the lowest IP address will be elected as the IGMP querier. So if we find ourselves in a scenario with a centralized IGMP querier, like we have here on Leaf 1, we end up with inefficient flooding of these periodic IGMP queries across the entire EVPN domain. So in order to solve this problem, each VTEP essentially becomes the master of its own domain, acting as the IGMP querier for each locally attached bridge domain. So in this model, the flooding of IGMP queries across the EVPN domain is eliminated. But even though we have the distributed IGMP querier and we suppress these IGMP queries, eventually, whether in response to a query or completely unsolicited, there's going to be a receiver that sends an IGMP join. So in order to ensure that all of the remote VTEPs servicing the bridge domain are aware of these interested receivers, the IGMP joins would need to be flooded across the EVPN domain. And this also results in inefficient, and in this particular scenario, redundant flooding of IGMP joins between all remote VTEPs. So the solution to this is where the Type 6 Selective Multicast Ethernet Tag, or SMET route, also simply known as the IGMP proxy route, comes into play. And if we take a close look at this route before we actually look at how it's advertised, we see that it will include the information necessary for a remote VTEP to populate its IGMP snooping and ultimately its MRoute table based upon the requested multicast feed, the information inside of the SMET route. So we see here that we have the actual source, if any, maybe it's a star comma G join. We have the group address, but then we also have the IGMP version, or versions in some cases, of the joins received for this particular group. So finally, in the OISM model, the route target of the supplementary bridge domain that's associated with the VRF that the receiver resides in will be included in the route. So let's actually take a look at this route in action. And as we do, we can start to get an idea as to why it's referred to as the IGMP proxy route, and ultimately why it's such a powerful new way for VTEPs to signal that they have locally attached hosts interested in receiving a particular multicast feed. So in this case, we have host 1 and host 2 both residing in VLAN 10. And they've sent IGMP joins, in this case, just star comma G IGMP joins, expressing interest in the 239.10.10.103 feed. Now, looking at leaf 1 here, instead of just flooding these IGMP joins across the entire EVPN domain, leaf 1 ends up suppressing them and instead sends out a single type 6 route into the EVPN control plane. So this route signals to all remote VTEPs servicing VRFA that, hey everyone, there are receivers in VRFA attached to me that are interested in receiving the star comma 239.10.10.103 feed. Now this is an important concept because it's going to lead to a few things here. One being that regardless of the number of hosts sending IGMP joins for the star comma 239.10.10.103 feed, leaf 1 is only going to send one type 6 route into the control plane. So this is host 1, host 2, this could be host 1, 2, 3, 400. If they're all inside of that same bridge domain, then at that point in time, if it's the same IGMP versions that are used in the joins, and it's the same star comma G group, that can all be suppressed and proxied into a single type 6 route. So that's within one bridge domain, but because we're actually leveraging the SBD route target in here, this actually holds true across all bridge domains in VRFA. So if another host, let's say host 3 in VLAN 30, also part of VRFA, ends up sending an IGMP join for this particular star comma G feed, if that star comma G maps to what's contained in the existing type 6 route, then there's no need to originate an additional type 6 route. So the question then becomes, is there a scenario where an additional type 6 route would be originated? And the answer to that is yes. So for example, if host 3 over here actually sent in a S comma G source specific multicast join via IGMP v3, then of course that doesn't align with what's in the existing type 6 route. Primarily here we have the star comma G. So for the S comma G, the SSM join, we would need to originate a new type 6 route for that particular join. But the same thing holds true. Let's say if some more hosts come online and they start sending IGMP v3 SSM joins for that particular S comma G feed, Well, then leaf 1 is not going to originate a new route for each one. It'll still go ahead and suppress and then proxy those into the type 6 route it originated when host 3 sent that original SSM join. So that was kind of a quick run through of the type 3 and the type 6 routes that we'll see in the actual control plane of EVPN with multicast. We'll go ahead and pause for questions there. So Alex, are there any outstanding questions out there we want to touch on before we keep rolling?
Yeah, so one question has come in, Mitch, which I think kind of naturally falls into this as well. So you've mentioned type 6. So where does the 7 and 8 routes fall into place here? So I think we're going to touch on this when we start going through the multi-homing. So it's a
yes,
perfect
indeed.
interlude onto the next section.
Yes, whoever asked that, thank you. You're a great setup, Ben. So leads right into our next challenge, which is exactly that. So now we have a scenario where the receiver is multi-homed via the active-active ESI model. So in this case, specifically, what happens if that receiver's IGMP join is received by the non-designated forwarder servicing that host's respective EVI on the ESI? So to tie that into our scenario here, host 1's IGMP join is hashed towards leaf 2. Now, leaf 2 is not the DF for VLAN 10 on this particular ESI. So two things need to be accounted for. The first is that it needs to inform all of the other VTEPs attached to this ESI that an IGMP join was received in the EVI of VLAN 10. The next is that we need to ensure that the designated forwarder, which in this case is leaf 1, needs to originate the type 6 route based off of this particular join. So as a quick reminder, I mean, the reason that we want the designated forwarder to originate the type 6 route is because the DF is ultimately who's responsible for forwarding any broadcast or multicast traffic for that particular EVI, in this case VLAN 10, onto the local ESI. So because of this, the DF must be the VTEP that originates the type 6 route into the control plane, because this is ultimately going to draw traffic to it instead of the other non-DF VTEPs servicing EVI VLAN 10 on ESI A. So in order to solve this, we can see right here in the diagram that what happens, let's go ahead and clean this up a little bit. What happens is when that join is received by leaf 2, who we can tell is not the designated forwarder for VLAN 10 on this ESI, leaf 2 is going to originate a type 7 join sync route, which is received and then processed by leaf 1. And the reason leaf 1 is going to import and process this route is because it's going to use a familiar value here that we saw in the previous session where we covered multi-homing, the ES import RT. It's not just for type 4s anymore. So for this type 7 route, we're using the ES import RT value to make sure that other VTEPs connected to ESIA import and process this route. Now we know, looking at the diagram, that leaf 1 is one of those VTEPs connected to this ESI, so it needs to import this particular route. So leaf 1 will import, process the route, and then upon processing the route, leaf 1 is going to add the local port channel interface associated with this EVI and ESI into its local IGMP snooping table. And then after this is done, leaf 1 will then originate the type 6 route. And as we saw previously, this is ultimately going to be informing the remote VTEPs of the locally attached receiver for this feed in VRFA being interested in receiving this particular feed. Now in this case, it's 239.10.10.103. Now notice that leaf 3 also receives the type 7 route, but it's not going to end up processing it because it's not looking to, it's not connected to the ESI, but specifically it's not looking to import any routes with this particular ES import RT. So what happens when a receiver actually ends up leaving that particular group? So similar to the previous scenario, we need a way for VTEPs servicing a common ESI to signal to each other any IGMP leave message received on a particular EVI. Again, in this case, the EVI is VLAN 10. So in this example, host 1 has decided it's time to leave this particular feed, 239.10.10.103. The host A sends that, and leaf 2 ultimately receives it, the non-DF. Once this is received by leaf 2, it will then originate the type 8 leave sync route. So very similar to the join sync, except this case it's going to be, hey, this particular receiver is no longer interested in receiving this feed. So the route is then going to be, again, imported and processed by leaf 1 since it's looking to import this particular ES import RT. And then once that's done, leaf 1 will, remember the distributed IGMP querier model, leaf 1 is going to send a query out on that local EVI and ESI to see, okay, hey, I received a leave. Is anyone out there that still wants this particular feed? So if no response is received within the query interval, then leaf 1 will ultimately withdraw its type 6 route associated with the star comma 239.10.10.103 feed. And then assuming host A is the last host in the VRF to lead this feed, and there's really no one left out there, leaf 3's IGMP snooping table can be updated accordingly based upon this withdraw. So I do want to pause there, though, because there were a few moving parts. We'll run through this real quick, and then we'll pause for some questions. In this scenario here, we just see that, okay, well, now that we have the control plane in place, the type 6 and type 7 routes, the multicast feed can be VxLAN encapsulated from leaf 3, sent into the EVPN domain, and ultimately delivered to our designated forwarder of leaf 1 for that EVI on that ESI. From there, it'll be sent out to the receiver. So I wanted to actually just cover that last piece before actually pausing for questions. So this time we really will pause for questions. I know there was a few moving parts there. So before we jump into the next challenge, Alex, are there any outstanding questions out there that we should address?
Yeah, two questions, Mitch. So one in relation to the multi-homing piece. So you discussed 6, 7, and 8. So which nodes actually have to support all three? So does every node in if you had an EVPN network, would all of them have to support the 6, 7, and 8 routes, or just a subset of them?
Oh, that's a good question. The VTEPs attached to that particular ESI are the ones, so just as in the previous session where we covered how the VTEPs that are connected to a common ESI are the ones that will originate, for example, the type 1, the type 4s. In this case, the same holds true here. So notice that leaf 3, it received the type 8. In this example, it received the type 7. It's not going to do anything with it. It's not going to import it. So the VTEPs that are connected to a common ESI, those are the VTEPs that will need to support these 3 routes in order for this to function correctly. Meaning, actually, let's take that a step further. What if this particular IGMP join from host 1 was received on leaf 1? So leaf 1 is the designated forwarder. In this case, one might think that, hey, just send the type 6 and call it a day. But leaf 1 connected to this ESI realizes that even though I'm the DF, there's still other VTEPs connected to this ESI and this EVI VLAN 10, that I need to make sure they realize that a IGMP join came in on this local segment. So even though leaf 1 is the DF, it will still originate the type 7, and it will be imported and processed by leaf 2 so that it can then populate its IGMP snooping table accordingly based upon which EVI and ESI that route was received. So the shorter answer to the question is, for those VTEPs connected to a common ESI providing routed multicast services, they all need to support these routes. But outside of that, maybe leaf 3 he's not connected to a particular ESI, maybe it's single home for whatever reason. It really won't originate or care about the type 7 and 8 routes, but it will of course care about the type 6 because that's how it's going to learn of the remotely interested receivers. So Alex, anything else you wanted to add there?
No, I think that's a pretty succinct answer. One other thing that was kind of came up a few times. So the question really was, again, looking at sort of the overall domain. You talked about what nodes need to support 6 and 7. Another question that came up was, what happens if I had a node in an environment that didn't actually support this new type 6 route? How would that interrupt?
Oh, good question. So in the IMET route, so let's say leaf 3 did not support this model for whatever reason. So the IMET route that would be originated by leaf 3, it wouldn't have the multicast extended community flags on the multicast flags extended community on any of its IMET routes. Next, it actually wouldn't have any of the PMSI tunnel attributes listed there for the processing of bull traffic. So it'd be the IMET routes that essentially we've covered up to the point of this webinar. If that happens, then if leaf 1, who does support multicast, receives that, it'll realize that, okay, well, leaf 3 can't support routed multicast, but I still need to make sure that multicast feeds within a particular bridge domain are delivered to him. So maybe there's an interested receiver hanging off of leaf 3 in VLAN 10 here, and host 1 is sending to that sending a feed within that bridge domain. We still want to make sure that that particular feed is still delivered to that remote host. It'll just use whatever the bum traffic forwarding method is for that EVI. It's just the routed multicast, the actual VRF aware routed multicast that wouldn't work to that particular VTEP in that case. Alex, anything you want to add there?
Sorry, Mike, I was typing answers. Sorry, no, that's fine. You cleared up the question. Thank you.
Okay, sure. Good questions. Yeah, keep them coming, guys. Okay. So up until this point, all of our examples have consisted of receivers and senders residing within the same bridge domain. So now we're going to mix it up a little bit. And just as we saw with the IGMP querier, the same issue can occur with the multicast DR for a given bridge domain. So in this case here, we have leaf 1 acting as a centralized DR for the environment. And this is going to lead to an inefficient forwarding model where all routed multicast traffic must hairpin through leaf 1 in order to be routed. Now, the solution to this is similar to our IGMP querier example as well, where we're going to essentially make use of a distributed multicast DR, where each VTEP acts as the DR for its locally attached bridge domains. So for example, in this case, host 5 is sending out a feed. It can be locally routed into VLAN 10 and then bridged out to the destination receiver, and then VxLAN encapsulated and sent into the EVPN domain to VTEPs that have originated a type 6 route for this feed. In other words, they have locally attached receivers. So it can be sent into the domain and then sent to the remote VTEPs. And then the feed is decapped and locally routed into the destination subnet and then ultimately bridged to the receivers. So again, the point being here is that instead of actually having a centralized DR, we want to make sure that every VTEP providing routed multicast services in the EVPN domain are capable of acting as essentially the last hop router attached to clients for multicast routing here, the last hop or first hop router, to perform that multicast routing. But then the question becomes, this is great, the bridge domain exists, so the VNI 10,020 is mapped to VLAN 20 on every leaf in this scenario. But the question then becomes, what if the bridge domain of the sender is not present on the egress VTEP? So for example, what happens now if leaf 1 and leaf 2 do not have VNI 10,020 locally defined and mapped to a bridge domain? So once the VxLAN encapsulated multicast feed is received, leaf 1 and leaf 2 would then inspect the VxLAN header, see a VNI that isn't locally present, they'll ask, how did I get this to begin with? And then essentially drop the packet. And sadly, host 1 and host 2 never end up receiving the feed from host 5. Now, for those familiar with the symmetric IRB model for unicast traffic, the solution here may seem to be, hey, let's use the layer 3 VNI when transporting the routed multicast feeds across the overlay. But this routing operation would result in header rewrites or changes to the header and TTL decrement of the multicast feed, which we do not want. So in order to ensure that there are no changes to the headers or to the TTL of all the VxLAN encapsulated encapsulated multicast feeds are bridged via whatever L2 VNI is associated with the sender's bridge domain. So I'm going to say one more time, that was pretty important. So in order to ensure, again, that we don't modify the headers, don't touch the TTL, all VxLAN encapsulated multicast feeds are bridged via whatever L2 VNI is associated with the sender's bridge domain. So by VxLAN bridging the multicast feeds, this overlay transport that occurs between VTEPs is transparent to the receivers, regardless of whether it's routed or bridged by the egress VTEP. So in other words, nothing we can do here. This is always going to be the actual VNI of the bridge domain associated with the sender. So again, the challenge is then, okay, well, we don't have that VNI locally present. How do we handle this? And this is where the supplementary bridge domain, which we alluded to earlier, comes into play. So the supplementary bridge domain, which is commonly referred to as the SBD, is a bridge domain that exists on all OISM-enabled VTEPs servicing a particular VRF. Now, there is a one-to-one mapping between the SBD and a VRF. And when OISM is enabled, the VNI associated with the SBD, in this case, in this example, we're just using VNI 50001, becomes the common bridge domain, which all VTEPs servicing the VRF will have locally present. So also note that there are no local interfaces attached to the supplementary bridge domain on any of the VTEPs. So knowing now that we have the SBD for VRFA present on all VTEPs servicing that tenant VRFA, we now have a solution to the problem that we faced in the previous example when that feed arrived on a VNI that leaf 1 and leaf 2 said, no idea, see you later, it goes to the bit bucket. So back to the example here, let's run through that again. Clear this off a little bit here. Leaf 3 is going to send this feed, and leaf 1 and leaf 2 are eventually going to receive that VxLAN encapsulated multicast feed. Now, when they look at this, when they actually take a look and decap and see that the VNI 10,020 is unknown, they can then map this feed to to the SBD that's associated with the VRF that the received VNI is mapped to. So in other words, the lookup and forwarding operation here is going to be done just from the perspective of VRFA. And then once this is done, the feed is locally routed into and then delivered to the receivers in those respective bridge domains. So I do want to pause for questions here, because now that we've gone through this and we've seen kind of the different pieces and parts of how this all comes together, let's actually take a pause before we actually jump into the lab and take a look at some of this in action. So Alex, any questions out there?
Yeah, so I think someone's drawn a question. Well, the analogy with the supplementary bridge domain to the IP VRF in a symmetric IRB model. Do you want to just kind of elaborate a little bit in terms of how the packets, or why we're actually bridging the packet, and therefore what effect it has on the multicast traffic as it is forwarded between the leaves, and therefore why it's not the same as like the IP VRF and the symmetric IRB? Sorry,
oh, sure.
Question.
Yeah, no, that's fine. That's actually it's worth noting that. So, because it is an important concept, because at least at first glance for me, I looked at this and I was like, whoa, symmetric IRB, that's the answer. But it wasn't, and the reason it was not the answer is because that routing operation would result in modifications to the header and ultimately a decrement of the TTL of that multicast feed, which we don't want. We want to make sure that that feed, after it's received across the overlay, VxLAN encapped and decapped at the egress VTEP, we want to make sure those headers and the TTL remain unchanged as they were when they left the original host, or the original sender, in this case, host 5. So by ensuring that we're always just going to use a bridging operation from the VTEP attached to the sender to the egress VTEPs, we know that the headers and the header won't be modified, and 2, the actual particular, how do I say this? The header will be modified and the TTL won't be decremented, which is what we do not want to have happen. So this is an important concept, and I think it's worth spending some extra time on this if we need. So Alex, is there anything you want to add there?
No, I think, as you say, I mean, the whole point here is that the OSM model, you remove it, well, it's all transparent to the end receiver, right? It doesn't know the traffic's being, where the traffic's been sourced from, doesn't know about the actual VxLAN transport going on here. So therefore, there's no extra additional hops here, no change in the packet. If it's been bridged, the only change happens when it's routed, and the change happens on the egress PE rather than on the ingress PE. So, yeah, I think we're good. Mitch,
okay.
We'll move on.
Okay, cool. A good question. Okay, so let's actually take the concepts that we've covered today and let's tie them into an actual scenario and get some feeds running. So before we jump in, we'll take a second and review what were our goals here before we just jump into the lab. Again, we're going to have host B and host C sending their feeds into the EVPN domain. So host B is in VLAN 20, host C is in VLAN 10. They're each going to send to their respective feeds 239.20.20.102, 239.10.10.103. Host A is connected active-active dual homing ESI model, and it's going to send an IGMP join for each of these feeds. Now, with a little bit of luck, cross our fingers, host A's IGMP join, we're hoping, hits our non-DF of leaf 2 for this particular EVI. Because then when that happens, we'll also be able to see the join sync route come in on leaf 1, which should then result in leaf 1 originating the type 6 to eventually signal leaf 3 that there are interested receivers attached to him. Okay, so let's actually take a look here and let's jump into our lab and get rolling on this. Okay, so first let's actually go ahead and take a moment and look at the IMET route, or IMET routes that are being originated, in this case, by leaf 1. So if we take a look at this, just as we saw in our example, leaf 1 is originating the IMET route associated with the SBD, where we see the particular route target and the VNI associated with that SBD, as well as the multicast flags indicating that this particular VTEP supports multicast routing, the IGMP proxy functionality. And we also see that there's an IMET route originated for the bridge domain, or the EVI of VLAN 10. Now this is important because what don't we see here? We don't see any IMET routes originated for the EVI associated with VLAN 20. Meaning in order for this to work, we need to make use of the SBD to then route the traffic into the proper destination subnet and then bridge it to the receiver once it's received. Because we know the traffic coming from host B, when leaf 3 VxLAN caps that and sends it over here into the domain, when leaf 1 receives it, it's going to see a VNI of 10,020. So actually, before we kick off any traffic here or any joins, let's go ahead and hop on spine 1 and make sure, so all these leaves here are connected by a single spine. Right now, there is not a single type 6 route that exists that's originating from leaf 1, which is expected. On leaf 1, let's actually keep an eye out for the join sync route that should be originated by leaf 2. And we should see that there's nothing here, and we do. So hopefully with a little luck, we'll have that IGMP join hit the non-DF so we can actually see this route. Actually, first, let's make sure that leaf 1 actually is the DF. So if we do show BGP EVPN instance, VLAN 10, we do see here that for this particular ESI, for the EVI VLAN 10, the designated forwarder in this case is leaf 1. So we've confirmed that leaf 1 is in fact the DF. Okay, so now that we have this here, let's jump over to leaf 3 as well. And let's go ahead and take a look here at his IGMP snooping table, which right now there's not much going on. So there's really no interested receivers anywhere as far as leaf 3 is concerned. All right, so now that we're actually paying attention to the control plane here and waiting for this information to update, let's go ahead and send the joins, the IGMP joins from host A. But before we do that, let's actually get our packet captures running here so we can see where does that IGMP join actually get hashed to, and then we'll also use the packet captures to validate that host A is actually receiving both feeds. Okay, so let's apply some filters here to cut out some noise. There we go. And then we'll go over to host A, and let's actually drop into bash here. We have 2 sessions open, so we can send a join for both particular feeds. And for the first one, we'll go ahead and send a join for the intra-subnet multicast feed, 239.10.10.103. And then over here, we'll actually send a join. So over here, let's say... Sorry,
Mitch, could you just put the topology on the right-hand side?
Oh, yeah, of course.
Right.
Yep, no problem.
Well, the topology, not the wireshark.
Yep, got you covered. All right, there we go. Okay, so now host A is going to send the IGMP join for the feed 239.20.20.102 as well. Now, if we look at our packet capture, while we were changing windows there, I believe I saw that the there they are. The IGMP joins coming in from host A are actually, hey, luck's on our side. They actually hashed out towards the non-DF, which we know based upon what we've seen today, that we should see a type 7 join sync route on leaf 1, and then we should see a type 6 route originated for this particular feed coming from leaf 1 on the spine. So let's look at leaf 1 first, and we see both of the expected join sync routes. Because remember, host A sent a join for the star comma G, the 239.10.10.103 feed as well as the 239.2020.102 feed. So we see both of those joined sinks that were from that particular ESI. We see the ES import RT right here, as well as the EVI associated with on that particular ESI. So that given the fact that Leaf 1 received this particular joint sync route, it should have, and it did, originate the type 6 SMET route into the control plane, and this is received on, in this case, the spine. So if we take a look at this, we see again that this is the feed that a host is interested in, and that host resides in the VRF associated with this particular supplementary bridge domain. In other words, when Leaf 3 receives this, it's going to know that a host in VRF-A, in this case, attached to Leaf 1, is interested in receiving these particular feeds. Now, regardless of who's sending to them, it's interested in joining these feeds. So if we go to Leaf 3 here and take a look at it, now we see that we actually have in the IGMP snooping table, we know via whatever VLAN behind the scenes is associated with the SBD, we know that, hey, there are receivers in VRF-A in the EVPN domain that are interested in receiving this particular feed. And if we look at this, this ultimately is what drives the MRoute table. Once we actually start sending the feeds, we're going to see the outgoing interface list modified here. So we've sent the joins. Let's actually get the feeds running now. So from host B, we're going to send a feed to 239.2020.102. And then from host C, we're going to send a feed to 239.10.10.103. Let's go ahead and kick these off here and take a look at Leaf 3. And now we see that the supplementary bridge domain, the SBD, is added to the outgoing interface list for these particular feeds. Meaning hosts in that particular VRF attached to a remote VTEP, which we know right now is Leaf 1, are interested in receiving this particular multicast feed. Now what we should see is if we go over to host A now, ultimately we have our routed multicast and the overlay model functioning here. So this is, we're capturing the link between host A and Leaf 1, and we see here that it is actually receiving both of the feeds. So in other words, we've accomplished our goal here. So before we actually wrap things up here, I do want to pause. Alex, any more questions based on that scenario?
Yeah, so one question that did come in was, and I don't think you did cover it, but what about external sources and like external receivers? How does this work? So really,
yes. So for the external sources and external receivers, say it's an external PIM domain, for example, there is the concept of a PIM edge gateway that's also a part of the drafts where we can have PIM running in the tenant to then from there connect to an external PIM domain. So maybe the IGMP join at that point in time, if a type 6 route is received by a VTEP, that is then realizes it's connected to a multicast router for that particular tenant. It can then make sure that that multicast router gets a copy of that IGMP join, and then from there, it can turn it into the proper PIM join upstream towards the RP. And the same thing would go for a source. So if a particular, if we knew a multicast router was connected to the edge of the tenant domain, and that multicast router then receives a copy of that particular source, it'll then send the appropriate PIM register to the RP, assuming it's an ASM model that's in place and an RP exists. Is there anything you want to add to that, Alex?
No, no. I mean, the point being there, right, is like what we're showed here in the demo is the sources and receivers are within the EVPN domain, but certainly is going to be a requirement for sources and receivers outside the EVPN domain. The likelihood and the model we're building here is like if they're in a PIM domain, then you can have sources in that PIM domain sending to receivers inside the EVPN domain, and you can also have receivers in that PIM domain receiving traffic from sources that are inside the EVPN domain as well. So it's kind of give pretty flexibility when we come to this standard. Back to you, Mitch.
Sure. All right. Any other questions out there before we actually wrap things up?
No, I think you covered everything, all the outstanding questions we had.
Okay, excellent. Well, in that case, everyone, that was we made it. It was a fun ride. Thanks again for joining. As usual, it was a lot of information in a short period of time, but we hope you found it helpful and maybe even enjoyed the journey along the way. So keep on the lookout for an invite to the next session where we'll be automating a VxLAN EVPN deployment via Ansible in the Arista validated design. And again, as far as session 7, let us know what you'd like to see. We're excited to see what this session ends up being. So thanks again, everyone, and stay safe.
Thanks, Mitch.